Okay, so now we'll try to filter an audio signal. First, let's read in our signal that we just recorded and listen to it.
Purimuunnos on ihan par.
Okay, it's a bit on the longer side, so we need to clip our signal. And maybe we could even let's take a look at the signal here and let's clip it first. We'll choose N. We'll use power of 2 length signals. So let's take N to be, for example, I don't know, 10 first. So it's like 1024 long. And let's take F equals F from 1 to 2 to power of N. And let's plot it. Let's see how this looks like.
Purimuunnos on ihan par.
Okay, this is quite short, but actually we should listen to the clipped signal. Clipped signal and plot it. Okay. It's very short, so I think we need to have more in our, let's take 2 to the 13. Do we still hear nothing? Yes, pretty much so. This is weird. Let's see what is the length of F here. So this is the length of the original signal and so it's something like 2 to the power 17 long. So maybe we'll take, so this should be roughly half the signal. Okay, so there is some silence first, so maybe we'll start a bit later, let's say 10,000 plus 1 to the 2n. Okay, there seems to be a lot of silence in the beginning, so let's
Purimuunnos. Purimuunnos on ihan.
Okay, and I think we can now shorten it, so if we take 2 to the 15.
Purimuunnos. Purimuunnos.
Okay, I think this is our signal, whose length is n to the n is 15, so we have 2 to the power 15 length, so our maximal frequency is 2 to the 14 in our FFT. So now we have our signal. This one is something old. Let's remove that one. Okay. So then let's take a look at the FFT of f. And let me first, before using this FFT shift thingy, let's just take a look at the FFT of f. And let's comment these still. So here we see the FFT coming out of the FFT algorithm, and it may look a little bit weird. Why is there a lot of stuff in the beginning and in the end of this vector? This is because of the internal workings of the FFT algorithm. It starts from the 0 frequency, then it's listed up to the frequency 2 to the n minus 1 minus 1, and then it starts again from minus 2 to the n and goes up to the very last point in this picture here would be frequency minus 1. So this is just the algorithmic way of organizing the stuff, and we can use the so-called FFT shift command, which will reorganize the FFT. So let me switch this one to this one, and now we see that this is maybe more useful for us to have the 0 frequency in the middle. So now this starts, so here the first one will be the frequency minus 2 to the n minus 1 here. And then it goes to lower and lower negative frequencies, hits 0 in the middle, and then frequency 1, frequency 2, frequency 3, and so on, until here, which is frequency 2 to the n minus 1 minus 1. And this is now a representation where we can start manipulating the frequencies. We can now filter the signal so that we can affect those frequencies we want to change. So for example, let's first try removing all low frequencies away from the signal. So frequency 0 and some frequencies around 0. And for that one, I think let's make a picture where on top we see this one, which is the original FFT, and then below that plot we see the one we have changed somehow. So let's do our first change of the FFT. So this would be FFT. So now, actually, let's put this one on top. Subplot 211, and then actually let's do it this way. Here, original. Let's put absolute value of the original FFT. So that would be this one. Let me call it FFT orig for original. That's that one. Then let's apply filtering. In the end here, we should have FFT filtered equals something, which we will do in a minute. And here we will maybe let's put even here. So this is the absolute value for plotting only, and this is also for obs. So this would be absolute value of FFT shift of FFT filtered, which we still have to compute. And here we will show this one, so we can compare. Maybe the top we can do in blue, and this one, the changed one, in red. But now we need to change, and we need to have a vector that tells us what are the frequencies in our FFT vector. So now let me call this nvec for vector for the frequencies n, and this vector starts from -2 to the power n minus 1, and then it goes up to, oh, so this should be capital N, and it will go up to 2 to the power n minus 1 minus 1. These are the frequencies, and let me just quick show you in the command prompt. If we take n equals 2, in that case our nvec is this one, -2, -1, 0, 1. But of course in our computation here we do have n equals 15, so it's much larger, the maximal frequency. But anyway, so here are our frequencies, and if we take this one is the FFT original is this one, and it's shifted. And then this is our vector telling what are the frequencies in the shifted domain. And then now we can take FFT original, let's say filtered. First, let's have it to be there's a little inconsistency here, well, because this is shifted as well, but well, like this, and then FFT filtered, and now we change, I'm changing this one to 0 only for low frequencies. So for those elements corresponding to nvec that are smaller to, let's say, 100. And actually we don't want to shift here at all. Let me try to save myself from this notation trouble. Okay, let's take a look. What happened here. Okay, this should be picture 2. No, this should be picture 2. Okay, not much change. Let's have a little bit bigger cutoff frequency here. 1000. Not so much change. 10,000. 100,000. Sorry, this should be equals 0. Nothing is changing. What I'm doing. What am I doing? Okay, I'm doing something wrong now. Let's see what's happening here. Here, this one. I don't know either. Let's see. Okay, now it's more like it. Okay. Okay, so maybe I'll just do it like this. Okay, and we should actually have here y lim. Oh, max from 0 to maximum like that, and also the same here, so we can see these two things on the same scale. So now actually I think let's do this in percentage. So let's go from 47% and up to 53%. Okay, so now you see I'm killing off 6% of the frequencies around the zero frequency, and now we would like to listen to the sound of the filtered signal. So now, okay, here this. So F filtered equals, so F filtered is this one, so we should do inverse FFT of, I think we need to shift this one. Let's see how my code works.
Purimuunnos.
In the end, FFT filtered. Why would it be? Oh, it's on capital.
Purimuunnos.
Okay, the second one contains nothing, so we need to let's do it also this way. Let's just check that this goes right.
Purimuunnos.
Okay, why does this not work? Let's put this a bit more. Maybe I'm removing too much.
Purimuunnos.
Okay, it should be real value, there's some complex part remaining from this filtering.
Purimuunnos.
Still nothing, come on. Sorry? Bit what? but there is no change yet. I mean, we only hear the first one. We're somehow, for some reason, we are not hearing anything. Ah, it is there. Okay. Good. So we have removed the low frequencies, and maybe we can let's do even more careful. So when we take so here I'm step by step removing the frequencies between 0. So you can hear that the low frequencies are going away. So what I did, I removed these really big components corresponding to the low frequencies, so you can hear clear change in the sound. Now I'm just wondering what on earth happened with this one. Let's try this again. Okay. Okay, now we start to hear something. So now it's kind of a bit more explicit what I'm doing. I'm taking away the frequencies whose absolute value is smaller. So I'm saying that take out all frequencies smaller than this number here. Let's just see what is this number to get an idea. 512, okay. So here if we okay, so now we have kind of a grab on the signal. So we are now removing frequencies whose number value we can put here. And now we can also do, this is a high pass filter. We are removing low frequencies. We could also remove higher frequencies. So then we are only leaving the low frequency. You see, I'm putting to 0 all high frequencies, only the middle parts are left. And of course we can kind of keep more. And then we could also have a kind of, so this, I showed you the low pass filter and high pass filter, but we could also have a band pass filter so that we remove stuff that's between two frequency limits. So let's say we remove anything bigger than 100, but smaller than 400, for example. So you see, I have removed here a frequency band. I removed these ones. And well, the sound changed quite a lot. Also, we could do something like from 300 to 1000. So you see, I introduced a band filter removing these frequency bands. So this is the way you get a grab on audio signals. Of course, it's not necessary to completely put something to 0. You can just maybe put it lower or higher, like we did with the music last time with the equalizer, where I kind of enhanced the bass sounds and damped the high frequencies. You can do all that. Now you have a complete control of the frequencies of your sound signal using this FFT transform. Okay. That was the frequency stuff I wanted to show you about audio signals, and after the break we'll go to images.